Thanks to all of you for sharing these great graphs that you guys picked off of the internet, all this data that we've got for the COVID-19 pandemic. This is really perfectly timed considering the next concept we're going into is exponential rates of change. So it's our first bit of nonlinear stuff. As unfortunate as this pandemic is, it's also the perfect application because this is what this unit is usually centered around, is the spread of a disease. So first of all, when you look at all of these, I picked a few of them off of Padlet. The thing that I wanted to point out is notice a really common theme that you'll see is, first of all these graphs are nonlinear, and they tend to be comparing different things like new cases or deaths or the effect, like this one down here, the effect of age on the death rate. You'll notice that nonlinear characteristic, that increasing steepening. So like on this one, so getting steeper and steeper when you look at confirmed cases. This one that separates it out by country, the hard thing is on this one is it's hard to see the very beginning of all these, but the United States is a good example of one where you can see that general trend of increasing steepness. And the thing we have to look forward to is, and I'll talk about this when we talk about exponential decay and stuff like that. Technically, this part of it up here is not exponential change when it starts doing this. I just want to point this out, that this is kind of what we're looking forward to around the country, and actually we've seen in a lot of places around the country, is the flattening of that curve as new infections quit ramping up. So right now, different parts of the country and different parts of the world are in different parts of the curve, but we can use other countries to kind of see what we should expect to happen if we kind of follow their lead. So anyways, like I was saying, you can see all of these have that steepening characteristic, and that's what we're going to look at when we talk about exponential growth, is that increasing steepness of the line. The graphs that we're going to look at and that we're going to model using equations aren't going to include the flattening part. There's some more advanced mathematics in there. We're going to look at the increasing steepness, but we're also going to look at the decreasing steepness. So again, you can see that increasing rate of steepness with this one as age groups go up. And then here is Washington. You can see that increasing rate of steepness. That's our exponential growth. And then we're also going to look at the tail side of this, which, as you can see in Washington, we're seeing. So we're also going to look at how we model and how we describe this thing that's happening here, this part of the graph here, and here. Those are the things that are the topics of this exponential change unit. Now, the other thing I wanted to talk about, this is that thing that they keep talking about, social distancing and the flattening of the curve. When we talk about a curve, whether it's a linear or it's nonlinear, they tend to refer to the slope of a line as a curve, the rate of change. And so when they talk about flattening the curve using social distancing and other tools like testing and infection tracking, they talk about flattening the curve. They're talking about changing the rate of change. So I know that there's a lot of talk about, I'm going to switch to this one, a lot of talk about, oh, this COVID-19, it's similar to the common, it's no worse than the common flu and stuff like that. But what I wanted to talk about was with the common flu has, just by the nature of it, it's an endemic disease, already has a very flat curve. So the common flu might look something like this. So we're more worried about this infection than the common flu, because the common flu tends to be, all the infections and the deaths tend to be spread way out. They start in maybe November, they last into the spring, into March and April. And if you think about a person with the common flu infecting others, we can refer to this infection diagram, showing the little people over here on the right. So the common flu, you might see spread occurring like this. Our COVID-19 would see spread like this. And the reason is because with the common flu, this guy right here, might have a flu shot. So we're not worried about that person. In fact, a lot of people get flu shots. You might have a couple of them with flu shots. This other person who's not getting it, this other black character, the red ones are the infected, the black ones are not infected, might be somebody who already had it earlier in the season and didn't realize it, so they already have immunity to it. Or maybe they just have a really strong immune system. They tend not to get flus very often. This happens with a lot of people. This happens to me. I get the flu every several years as I watch it go through our schools and stuff like that. Um, so it tends to be really, really spread out, and our hospitals have been dealing with this rate of infection for decades. It's sort of the normal thing that they're prepared for. The reason COVID is different is because um, notice for COVID, nobody is immune to it. Okay. And one of the big things that's scary is with COVID, you can be carrying it around, passing it around without actually showing symptoms. The flu, you tend to see symptoms really quickly after you catch it. COVID, not so much. So you can really pass it on easily. And then once you're out there and you're passing it on, there isn't anybody out there with immunity to it yet, or there's very few at this point. The percentage of the population that's had it's really low. And so that's why, unless we do something so that COVID spreads slowly like the flu, we would see this huge explosion in infections. It popped up all of a sudden in January. Instead of being spread out, COVID would be happening in a very short span of time. And nobody has immunity to it. So you have a much more rapid increase in infections and deaths. People are severely ill. And our hospital system is not prepared for that. They talk a lot about, personal protective equipment and respirators and stuff. We can handle it when it's the normal spread out sort of trickle of flu cases coming through, and it spikes a little bit now and then. But with COVID-19, we are nowhere near prepared. So all the social distancing and stuff like that, and then we'll talk about vaccines, treatments, testing, and tracking a little bit. All the things that we're doing, we're trying to make it so that COVID infection slows down like a flu infection. And since no one's immune, the only way we can do that, prevent that rapid spread, is to not touch each other, to stay away from each other, so that it goes slowly through the system so the hospitals can handle it. So anyways, the other thing I'm going to talk about here is how this relates to modeling exponential change. And so we want to be able to write an equation and predict, how the infection is going to spread. So another way to look at this diagram, this is a characteristic of diseases. You can actually look at this as different diseases and how they spread and how contagious they are. You could also say that maybe this is an example of like Ebola. Tough to pass on. You really have to be in close contact with some of these bodily fluids to pass on Ebola. Maybe this is a common cold, a lot more contagious. You can pass it with a sneeze, and you can't get a vaccine for it and stuff like that. Although some people are just prone not to getting colds. So you have people who aren't going to catch it even when they're exposed. Whereas this is your COVID-19. Again, nobody has immunity to it. It's pretty easy to spread. You can spread it just by sneezing near somebody. And so notice what happens on this one, the first one, Ebola, maybe. I'm just using this as an example. One infection leads to two more infections. One infected person leads to two infected people. Those two infected people, in turn, infect two more people. So this person would go on and infect two more people, and this person would go on and infect two more people. Common cold, a bit more contagious, so each infected person is infecting three more people, and then each of those people infects three people. You can see that one spreads a lot faster, and then COVID, the one that we're really worried about, each of those infected people infects five more people. Now this is a bit exaggerated. This is really on the high end for COVID. COVID is actually more in their scale of one person infecting three more people. But this would mean every one of these infected people would infect five more people. That's a really, really fast spread. That's actually more like the spread of measles or something like that. And so that's the number that we're going to look at when we're looking to make an equation to model um, this change in part C. And as another application and extension of this, I just wanted to show that this number I'm talking about, that multiplier, you can see all these different diseases have different multipliers. So measles is incredibly contagious because it's airborne. It doesn't even need to have like droplets. It can just spread through particles in the air, which makes it extremely contagious. If you go down to smallpox, a little bit less contagious, but still very contagious. Notice the ones that are spread by airborne droplets have higher numbers, but where you have something like bodily fluids or saliva, a lot less of that happening. You don't just happen to do that when you're at the grocery store. These are people that you're near. They have lower infection rates. So this is the number of infections per one infected person on average. Whereas the influenza, you can see right down here, COVID is up here, 1.5 to 5.7. The normal influenza is somewhere about 0.9 to 2.1. Seasonal strain, so it changes every season. And so these are really important numbers when we start looking at how a disease spreads and making predictions about how many people are going to have that infection as things spread.